Hello student, here we discuss about the stability order of enol form. It's from its diketone. These are three different diketones are there. Here here is methionine group, here one H and one CH3 group, here one H and one third butyl group is there. So here I have shown you this structure is like this. Two alpha hydrogen here one alpha hydrogen, here one alpha hydrogen. So they are asking criteria to find the stability, number of alpha hydrogen in enol form. Here due to key diketone, here in enolic form, conjugation intramolecular hydrogen bonding as well as resonance. Extended conjugation mode will be the extended conjugation mode will be the stability. And lastly, when number of alpha hydrogens are equal, at that time hyperconjugation factor works. Okay, so first of all find the number of alpha hydrogen in given diketone. Here we have seen that it is 8, here 7, here 7. Now question arises for again last how we can get the stability of these two which are having same alpha hydrogen, same number of alpha hydrogen. So we will see that first I will tell you this after when base will be there. So when base will be there, so this is getting deprotonated, and then at the time this will this will be removed, this H will be removed, and when H proton will be removed, at that time there will be negative charge. Okay, so I put one negative charge. Earlier it was 2 hydrogen, now it is only 1 hydrogen with 1 negative. And then why this is going on? Because oxygen is more electronegative than carbon, so attract share of electron towards itself. So it will take away this pi electron and form this single negatively charged oxygen will be. So this hydrogen is cleaved, proton is cleaved from here, deprotonation will take place with the help of base, and the bond between this carbon and hydrogen will break and form new bond between this carbon and this carbon. So in this way we will get enol. Okay, so after the loss of this one proton, we are getting this form double bond, and then this proton which we lost, it is grabbed by this oxygen. Okay, so we'll get enol. So in this way we get keto enol tautomerism. Now we will see here in the same way this hydrogen is lost, everywhere the same way hydrogen is lost, one negative charge will be there, and oxygen grab the electron, and then it will having negative charge. So this electrophilic carbon, this bond is breaking over here, and we'll get enol. And now we will see that there will be intermolecular hydrogen bonding. Surprisingly, in all these three cases there will be intramolecular hydrogen bonding occurs, so which stabilizes the enol form. But which will stabilize the enol form more depends on three factors: that number of alpha hydrogen in diketone which we have seen that it is having A is having most stable enolic form. We have to compare second and third. Second and third means which is having one CH3 group and which is having one third butyl group in the here. Third butyl group. So we have to compare this. Okay, so here we will see 7 alpha hydrogen are there, and when base is taking away this proton, this proton is kicked away, and this bond is going to form here because oxygen grab the pi electron towards itself. So it will oxygen get negatively charged, so it will be electron deficient. So H positive was taken away by base, and lone pair of electron which are left behind will form double bond with this. So we'll get enol. See, we'll get enol. Okay, now here one CH3 group is there. Remember, all structures are same, only here we have to make a line, and then we will find out, okay, this is the structure. And double bond, single bond, double bond, there is conjugation of double, single, double bond, and there is intramolecular hydrogen bonding occurs. So here there is CH3, so there is 3 hyperconjugating structure are there. Okay, and 3 here and 3 here, total 6 hyperconjugation structures are obtained. 3 plus 3. Okay, 6 hyperconjugating structure. 3, and that time we are watching only this olefinic carbon, 3 alpha CH3 and 3 alpha in this CH3. So total 6 hyperconjugation structures are there. So it will be more stable in enolic form as compared to third butyl. See why I am saying third butyl is less forming less stable enolic form, because here only 3 alpha hydrogen and no alpha hydrogen in this, because when we are discussing about hyperconjugation, we have to see only alpha hydrogen of the alkene. Okay, which is alpha to the double bond. So here only 3 alpha H. So enolic form is having less hyperconjugating structure. This methyl form is having 6 hyperconjugating structure. This is having only 3 alpha hyperconjugating structure. So order will be 1:2:3. 1 we have seen 8 alpha hydrogen in diketone, that's it. And here 7 alpha hydrogen. So we will see the enolic form. Here hyperconjugating structure is 3 plus 3 6. Here only 3. So more will be the hyperconjugating structure, more will be the stability. So 2 structure is more stable as compared to 3 enolic form. So first most stable enolic form, then second and third, and second is having more stable enolic form than third. Okay, in this way we can see that how easily we can go, and everywhere there is intramolecular hydrogen bonding. See, this is having intramolecular hydrogen bonding, this is also having intramolecular hydrogen bonding, this is having also intramolecular hydrogen bonding. All of them are having conjugation. So there are 3 factors which are governing the stability of enolic form. Thank you for watching. God bless you. All the best.